Hello students, welcome to EPG Pathshala. I am Professor Panchapakeshan from University of Delhi. Today we are going to discuss about the module Application to the Hydrogen Atom. This is from the paper Radiation Theory in the course on Physics. After studying the module, you should be able to understand how selection rules for transitions are obtained by evaluating matrix elements and finding when they are non-zero. You should also learn how the lifetime of an excited state of hydrogen atom is calculated. You should also become familiar with energy values of the states of hydrogen atom. You should also learn a bit more about calculating with natural units. You have studied the energy spectrum of hydrogen atom. We would like to apply the framework developed so far to the concrete case of the hydrogen atom. We shall consider first when a transition from the one state to another state is allowed. The states are labeled by the total quantum number n and the orbital quantum number L and the azimuthal or magnetic quantum number m. If the initial state has values of n, L and m and final state has values of n prime L, n prime, L prime and m prime, we find that the change delta L has to be plus or minus 1 and the change in delta m can be 0 or plus or minus 1, and these are the only values allowed for delta L and delta m. These are called selection rules and are derived by using the properties of spherical harmonics or associated Legendre functions. We next study the specific transition in hydrogen from the state of 2p with L equal to 1, the first excited state, to the ground state 1s, which has got L equal to 0, which is the ground state. As L is equal to 1, this transition is allowed. So also for change in m. We carry out the calculation using the well-known expressions for the wave functions for both the states and obtain the transition probability. The lifetime of the excited state is just the inverse of the transition probability. The calculations are especially simple if we use the natural units, in which case h cross and c are 1. We discuss the use of such units in calculations in the last section more fully. We go on in this module to apply some of the things we have learnt to the hydrogen atom. We first begin with the selection rules. We apply our formalism to the electron bound in the hydrogen atom. We consider the structure of the matrix element between B and A of X vector, where the initial state A is characterized by the wave function. The wave function can also be written as the bra and ket of X vector with A, which is given in terms of the variables of X vector then, namely r, theta and phi, and this is equal to capital R n L of X y Lm into theta phi. Y capital R n L is the radial function and y Lm theta phi are the Legendre function, generalized Legendre functions involving theta and phi. The final state is similarly written as the bra and ket, bra of X vector and ket of B, which is equal to the radial function of n prime and L prime of X and the y Lm function of y L prime m prime of theta and phi. And X has components which is written in terms of r theta and phi, so we have X is equal to r sine theta sine phi, y is equal to r sine theta cos phi, z is equal to r cosine of theta or r cos theta. The matrix element of Z between the states B and A can be written as integral over R into capital R, the radial function of n prime and L prime, into the radial function of n and L integrated over d of small r. And similarly, integral over the function y L prime m prime into cosine of theta into y L and m. Y L prime m prime comes from the final state and y L m comes from the initial state, and cosine theta is the term that comes from the z coordinate r cosine of theta. Now, integral of y star L prime m prime into cosine theta into y L m d of cosine theta d omega, this is what this becomes. This can then be written as p m prime L prime cosine theta. This is the Legendre function into exponential minus I m prime phi into p ml cosine theta of exponential I m phi into cosine theta d cos theta d phi. So we have an integral over p m L prime and p m L cosine theta multiplied by cos theta into 2 cosine theta, and the d phi integral has made both the m's the same, m equal to m prime, with the delta function m prime, and gives us a factor 2 pi in addition, and this is equation 3.5. Where p ml cos theta are usually called the associated Legendre polynomials, using the recurrence relation that 2l plus 1 cosine theta into p ml is equal to L plus m into Pm of L minus 1 plus L minus m plus 1 into Pm into L plus 1. So we can write the Legendre function Pml multiplied by cos theta in terms of Pm of L minus 1 and Pm of L plus 1. We have the integral over Pml prime and Pml cosine theta d cos theta becomes Pml prime cosine theta 1 over 2L plus 1 L plus m Pm of L minus 1 and L minus m plus 1 into Pm of L plus 1 d cosine of theta. From the orthogonal property of the associated Legendre polynomials, we are using omega, or rather the script w for cosine theta. We have integral over minus 1 to plus 1 Pmlw into Pml prime w into dw is equal to 2L plus m factorial into 2L plus 1 into L minus m factorial into delta of L prime. Using 3.8, equation 3.7 gets simplified as integral over Pml prime w into Pml prime dx is equal to L plus m into twice L prime plus m factorial divided by 2L plus 1 into 2L prime plus 1 into L prime minus m factorial into delta function of L prime and L minus 1 plus L minus m plus 1 into 2 L prime plus m factorial divided by 2L plus 1 2L prime plus 1 into L prime minus m factorial into delta L prime of L plus 1. So we get two terms, one with delta L prime L minus 1 and the other with delta of L prime and L plus 1. Therefore, the integral over dw from minus 1 to plus 1, 0 to 2 pi d phi Pm prime L prime into w into Pml into exponential minus m prime phi plus Im phi gives us summation over L and L prime integral over minus 1 to 1 dw Pm prime L prime w Pmll into 2 pi into delta m prime, which becomes 2 pi into two terms, one involving delta L prime L minus 1 and the other involving delta L prime L plus 1. And of course we have the delta of m prime coming from the phi integral. This becomes 4 pi into L plus m into L minus m plus 1 factorial delta L prime L minus 1 divided by 2L plus 1 2L minus 1 L minus m plus 1 plus L minus m plus 1 into L plus 1 plus m delta of L prime L plus 1 and denominator 2L plus 1 2L plus 3 L plus 1 minus m factorial. Equation 3.4 thus gives, which is the matrix element of Z between B and A, as 4 pi multiplied by summation over L prime summation over m prime, delta of m prime into r cubed, radial function of L prime L minus 1 into radial function of NL into L plus m divided by 2L plus 1 into 2L minus 1 into L minus 1 minus m factorial multiplied by L plus 1 plus m plus delta function of L prime and L minus 1 plus r cubed into delta function of L prime and L plus 1, and again two radial functions, one is r n prime L minus 1 and another is r n L, and L minus m plus 1 into L plus 1 minus m factorial divided by 2L plus 1 into 2L plus 3 into L plus 1 minus m factorial. This is equation 311. Thus, the matrix element of Z between the state of the atom A and the state of the atom B, that is bra B Z ket A, is non-zero for L prime is equal to L plus 1 or L prime equal to L minus 1. So, L prime minus L equal to plus or minus 1, or delta L, the change in the L values, is plus minus 1. This is due to the fact that the photon is a spin 1 particle, and so the L value has to change by delta L equal to plus or minus 1 or 0. The 0 value is ruled out as there has to be a change in parity in going from A to B state. When we consider x and y components, that is sin theta sin phi and sin theta cos phi, we get a change in m also by plus or minus 1. Thus, m prime minus m, which is denoted by delta of m, can be 0 or plus or minus 1. These are then the selection rules for transitions from Lm to L prime M prime states. Thus, we see that in the dipole approximation, only those transitions are allowed for which delta M is equal to 0 plus or minus 1 and delta L is equal to plus or minus 1. If the initial state A is having quantum numbers n, L, m, and the final state has quantum numbers n prime, L prime, m prime, then the transition probability per unit time is given by transition probability, or omega, for A going to B plus gamma is equal to E squared into omega cubed by 3 pi into the square of the matrix element of x vector between B and A, where the matrix element of x vector between B and A is given by the relation 3.11 with the restriction 3.12. If for some values of n, L, m and n prime, L prime, m prime, the matrix element of x vector between B and A is equal to 0 for the state B, EB being lower than the energy EA. We have to go back to the plane wave expansion and take the next term in the expansion for exponential minus ikx, which is 1 plus or minus ik vector dot x vector and higher order terms. And the matrix element then becomes matrix element of between B and A, or bra B and ket A, of the quantity I into k vector dot x vector multiplied by p vector dot epsilon lambda vector. We shall consider these cases, which are the higher order terms, later. We then go to the first excited state. Let us consider the radiation emitted in going from 2p state of the hydrogen atom, which decays into the ground state 1s. Here 2p state is given by r, radial function of 2, 0, into y, the associated Legendre function of y 1, 0, theta of phi, and 1s state is given by r 1, 0. So, the matrix element of Z between B and A can be written as small r into radial function 2, 1, radial function 1, 0 into small r squared into dr and then integral over d cos theta and d phi of y10 star cosine theta d cos theta d phi. Therefore, this is equal to 2 pi into integral over d small r of r into two radial functions 2, 1, 0 and 1, 0 into r squared and multiplied by 1 over square root of 4 pi and square root of 3 over 4 pi and the integral from minus 1 to plus 1 of cos theta into d cos theta. And so the whole thing becomes 2 pi into root 3 by 4 pi into 2 by 3 into integral over d small r of r into capital R21, capital R10 into r squared as integral over cos theta gives 2/3. So the matrix element of z between b and a can be written as 1 over square root of 3 into integral over 0 to infinity of small r cubed into dr into R21 into R10. This we call equation 3.14. The radial functions R21 and R10 of the hydrogen atom can be found in almost all the books on quantum mechanics. We simply write them down here. That is, R21 is equal to exponential 1 over 2 a naught 3 by raised to the power 3 by 2 into multiplied by r divided by square root of 3 into a naught exponential minus r by 2 a naught. R10 is 2 divided by a naught raised to the power 3 by 2 into exponential minus r divided by a naught. A naught here, of course, is the Bohr radius. Now, r into R21 into R1 naught into r squared dr from 0 to infinity can be then written as an integral over R4 dr exponential minus r by 2a naught minus r by a naught. This is equal to R4. The extra r, R4, comes from the R21, which is in the numerator a term r. So the whole thing is an integral over R4 dr exponential, and it gives us it can be written also in the form 1 over root 6 a naught 4 into twice a naught by 3 raised to the power 5 integral from 0 to infinity of x4 dx exponential minus x. As the integral is a gamma function, the right hand side is gamma of phi into 2 raised to the power 5 a naught divided by root 6 3 raised to the power 5 in the denominator. Now gamma of phi is equal to 4 into gamma of 4, which is equal to 24, and therefore the integral from 0 to infinity of small r into R21 into R10 into r squared into dr is given by 2 to the power 8 a naught divided by root 6 into 3 to the power 4. Therefore, from 314 and 317, we get the matrix element of z as 2 to the power 8 a naught divided by 3 to the power 4 root 6 into root 3. The binding energy expressions are then obtained as follows. The binding energy values of the ground and excited state are given by the equation En is equal to minus alpha squared m by 2n squared. A naught is equal to 1 over alpha m is the Bohr radius. Alpha is e squared by 4 pi and m is the mass of the electron. So omega, which is E2 minus E1, is minus alpha squared m by 2 into 1/4 minus 1, which is equal to 3 by 8 alpha squared by m. We call this equation 318. If polarization is along z-axis, the transition probability per unit time is thus obtained by using the equation 313, 318, 314, 317 as follows. The transition probability, or omega, for p going to s plus gamma is equal to e squared into 3 by 8 alpha squared m, the whole thing whole cubed, divided by 3 pi into 1 by 3 into 2 raised to power 16 a naught squared and divided by 6 into 3 raised to the power 6, the whole thing whole squared. And this, when you work it out, we get the transition probability for p going to s plus gamma is equal to 2 to the power 8 alpha to the power 5 into m divided by 3 to the power 7 into 1 by 3. So far we have taken the contribution of the matrix element of z only. If we include the x and y axis directions of polarization, each direction will contribute 1 over square root of 3, And so the sum over all the polarizations and the average over the initial polarizations gives us the same value as the equation 332. This is shown in equation 333. Here we have L equal to 1 and M takes the values 1, 0, minus 1. Thus the formula 332 for the transition probability from P state to S state plus photon does not change. Thus the transition probability per unit time is given by 2 to the power 8 alpha phi m divided by 3 to the power 7 into 1 by 3. Lifetime of excited states. As the transition probability has a dimension of inverse of time, we can find the lifetime tau of the excited state. We can thus calculate the lifetime of P state going to S state, or tau of P going to S plus gamma, by inverse of the transition probability for P going to S plus gamma, or equation 334. Thus, for the mass of the electron, m, which is equal to 1 over 1.3 into 10 raised to the power 21 seconds, the transition probability or the lifetime for the decay of the P state into the S state plus a photon is given by 1 over transition probability for P going to S plus gamma, which is 3 raised to the power 8, 137 raised to the power 5 divided by 2 raised to the power 8 multiplied by m in the denominator. This is equal to 1.237 into 10 raised to the power 12 into 1.3 into 10 raised to the power minus 21, and this gives us 1.6 into 10 raised to the power minus 9 seconds. This is called the lifetime of the excited state 2p, and you can see it is of the order of 10 raised to the power minus 9 seconds. Calculations using natural units. The mu meson, or muon as it is often called, decays into 3 particles. These are the electron and 2 neutrinos, one of electron type nu e and other of muon type nu mu. If lifetime of tau of muon decay is given by the formula 1 over tau is equal to gf squared into m phi divided by 192 into pi cubed, where m is the muon mass, 106 MeV, we would like to calculate the dimension of gf in natural units. As tau inverse has same dimensions as mass or energy, gf squared has dimensions of 1 over m4, so gf has dimensions of m raised to the power minus 2. If gf is equal to 1.166 into 10 raised to the power minus 11 MeV raised to the power minus 2, we can calculate the lifetime for tau for mu decay. Mu is known, tau mu is equal to 192 into pi cubed divided by 1.166 into 10 raised to the power minus 11 squared, and putting in the numbers as shown here, as 1 MeV can be written as Me over 0.511, we get it as 1.1 divided by 0.66 into 10 raised to the power minus 21 seconds, or the tau is equal to 2 microseconds. So we get the decay time of the muon as 2 microseconds. As you know, the muon roughly has this kind of time decays. So students, let us summarize what we have learnt in this module. In this module, we have applied our formalism to the hydrogen atom, which has 1 electron. We have obtained the selection rule by considering the wave function of the atom as product of radial function and spherical harmonics. The properties of these functions give the selection rules or permitted changes of L and M. These selection rules are, as we have seen, delta L should be plus or minus 1 and delta M should be 0 or plus or minus 1. We studied the transition from 2p to 1s state of the hydrogen atom and calculated the transition probability per unit time. The final integral becomes a gamma function integral. The inverse of the transition probability gave us the lifetime of the excited state 2p as 1.6 into 10 raised to the power minus 9 seconds. the calculation was done in the natural units, and you saw how it got simplified. We then learnt a bit more about working in natural units and calculated the lifetime of muon decay also, which came out to be about 2 microseconds. Thank you so much.